Welcome back to Coronavirus University. It's been a minute. I wanted to look a little bit at the geometry of linear maps, which is what I call linear transformations. It's a lot easier to write linear map than linear transformation. So that just means the same thing as linear mapping or linear transformation or any of the other words that might be used in the book. It's what I use. It's a lot of people call it that. Anyway, if you've seen our good friend John's nice lecture on the last section of the chapter, you've probably been asked to try to understand the standard matrix for a rotation by angle theta, rotation of the plane R2, and he gave it to you, and I think he mentioned there's a little bit of trigonometry involved in that, and it's good to draw a picture like this and try to figure out the trigonometry. In fact, I'll give you a little hint. If you let this R, let me just call it R. I'll drop the theta subscript, but you can think of it as indicated by a subscript if you want to. The picture I have the plane thought of as the domain of the linear map, and I have another picture of the plane with the codomain, or some people actually call that the range, but we won't get into that. And of course, a linear map takes 0 to 0. So I'm thinking of the origin, 0, 0 going to 0, 0. And what do you do to figure out the matrix, the standard matrix for this linear map? Well, you want to see where the standard basic vectors E1 and E2 go. And I've drawn a picture of that. And so to aid your trigonometry, you might want to put in the original E1 and the original E2, the axes there, as it were, and ask yourself, what's this angle? What's that angle? Just a hint there. As far as notation, the book likes to give the linear map a name, typically T, and then the matrix that we call A. Sometimes you want to connect them together, and a notation I like is actually to just put square brackets around this. And so this is supposed to be the matrix. Or should I say, the matrix. Anyway, the matrix of R. That's another way of thinking about it. Just if you want to distinguish between the linear map as an abstract idea of a mapping from R2 to R2 and this array of numbers. Okay, let's look at a special case. This is actually in honor of John. In fact, in honor of John, I'm going to call this special case J, this linear map. And here's a picture of what J does. So this is J applied to E1 and J applied to E2. I think won't fuss with the colors now. Okay, so what did that map do? What is that map? Well, it took this, let me call this a frame, and it rotated it counterclockwise by an angle. What was the angle? The angle, the angle here, this is R pi over 2, or R 90 degrees. And I'm going to call that J. So J is actually the name for counterclockwise rotation by a quarter turn, pi over 2. Okay, so quarter turn. Okay, that's the standard notation for that, actually, used all over mathematics, J. And so what is the matrix? Well, you could figure out J by plugging in theta equals pi over 2, and I'll let you do that if you want to. Or you could simply look at where things go. So where does E1 go? So E1 goes to E2, right? That's what I'm seeing here. J of E1 is E2. This is another way to sort of write it. And J of E2 is where? J of E2 is minus E1. So E2 goes to minus E1. It's just another way of writing these statements here. It's kind of useful sometimes to do that. So what does that say the matrix for J is then? J, it's matrix if you like. Well, its first column is going to be J of E2, right? That's going to be J of E. E1. And the second column is going to be J of E2. And that matrix is exactly what matrix? Well, it's the matrix 0, 1. This is E2, 0, 1. And this is minus 1, 0. So there's the matrix J. That's the J matrix. And I may actually just drop those square brackets from time to time. Okay? Okay. So what's kind of interesting is that what does that say about this matrix here, the rotation by angle theta? Maybe I'll put the theta in that one. So this implies I can write R of theta, put the brackets around it if you like, as what? It's cosine theta times the identity matrix, 2 by 2 identity matrix, plus sine theta times this matrix J. So maybe I'll put brackets around it just to remind you I'm talking about a matrix here. Okay. So in some sense I can represent, this is the 2 by 2 identity. Remember that what that matrix is? That's this matrix here. Whoops. Getting ahead of myself. 1, 0, 0, 1. And this matrix here, right? The matrix we have up there. Yeah. 0, 1, minus 1, 0. Okay. So I've written a rotation matrix as, if you like, a linear combination with weights, cosine theta and sine theta times the rotation by no degrees at all, the identity, and rotation by quarter turn. And I think that's kind of an interesting fact. So you might think about that more. In the next lecture, I want to look at what happens when we go from rotations of R2 to rotations of R3.